Okay, so moving on from plotting polar coordinate points, I have rectangular equations in front of you on the front side of the sheet, and on the back side of the notes there's polar. So we're going to start taking equations and changing them back and forth into the other type of equation. The key pieces we have to remember are those same four formulas. This is on the back bottom side. Those four key equations. So the rectangular to polar is quite simple because all we're going to do is replace the x with r cosine theta and replace the y with r sine theta. And then rectangular coordinates, or rectangular equations I should say, are usually solved for y. Polars are solved for r. So we try to get r all by itself, which here is going to happen by factoring out the r and then dividing over the binomial. So if I divide over the cosine theta plus sine theta on both sides, my equation is going to be r equals 5 over cosine theta plus sine theta, and that's the polar equation of that linear graph. Now we'll get into how to graph these moving forward, but right now we're just working on seeing the equivalent equation, then I'll prove to you later how they are the same line in this case. On the second one, you got a couple options. You could substitute in right away, r cosine theta for x, r sine theta for y, square them out, and get r all by itself. Although I'm going to do something slightly different just to show it as an option. I'm going to square this out first. And the reason I'm going to do that is because I have now an x squared plus y squared. And one of our equations is that x squared plus y squared equals r squared. So I'm going to go ahead and just replace the x squared plus y squared with an r squared. Minus the 2x would follow, but I'm going to get rid of the x and replace it with r cosine theta. And then I have the plus 1 equals 1. Then, of course, subtract 1 from both sides, and that'll take care of that. And then here again, I can factor out an r. So this is actually going to be teed up just like we have done in the past. So either r equals 0 or r minus 2 cosine theta equals 0. Now, if I'm teeing it up and then solving for r, this second equation is going to read r equals 2 cosine theta. So anytime we have really kind of, it looks like two equations. And actually the two of those paired together would actually be an equivalent. But r equals 0, think about the graph of something where the radius is equal to 0. On our coordinate plane, coordinate system, the polar one, r equals 0 is just this solid point right in the middle. So this is going to include that point when r equals 0 for theta values of pi over 2, because the cosine of pi over 2 is 0, so 2 times 0 would be 0. So this includes this one anyway for theta values like pi over 2 and 3 pi over 2, and this is for all theta values. This equation is good for all theta values. So you really don't need this. You don't want to be redundant and include that, since when theta is pi over 2 and 3 pi over 2, it will already include an r equaling 0 in those scenarios. So we will include that point eventually anyway. So this will be our only, if you look in the back of the book on your solutions, that's why you won't see a lot of times the other one that you got, because it's redundant and it's already included in and amongst this equation. So again, going from rectangular to polars is very simple because you're just subbing in your r cosine and your r sine and then solving for r. You have to be a little bit more creative on the converting polar into rectangular. So things you want to look for are r squareds, so that you can take them out and replace them with x squared plus y squared. Look for r cosine theta, so you can take it out and replace it with an x. R sine theta can be replaced with y, or look for y's over x's, or I'm sorry, look for tangents of theta that can be replaced with y's over x's. So you're looking for opportunities to get x's and y's in there when you're translating to rectangular. So if we take this first one, for example, if If I square both sides here, now I have r squared equals 25. Well, r squared from one of our formulas below is the same thing as x squared plus y squared equals 25. And that, as you know, is a circle centered at the origin 0, 0 with a radius of 5. That's what r equals 5 is going to look like. Any point that has a radius of 5 is going to be a circle with a radius of 5. So there's your rectangular version. There's your polar version that we came from. In B, we have a theta that we're trying to get rid of. So, like I said, tangent of theta is a nice opportunity because we can replace that. So on this particular one, we can take the tangent of both sides. So the tangent of theta can be replaced with y over x, and the tangent of pi over 4, we should all know, is 1. So if we just multiply both sides by x, you get the line y equals x, and that's the rectangular equivalent of that. If you think about, just on a side note, where theta equals pi over 4 lies, that's right there. Theta as a pi over 4 paired with positive r's, theta as a pi over 4 paired with negative r's would be down here, creating the line y equals x. So both in the polar thought process and the linear thought process, that graph coincides with that graph. This next one is different because we have a cosecant, and we can't really do much with cosecant, but we can change cosecant into 1 over sine, so that would make this 3 over sine theta. And then we don't like things in the denominator really usually ever, so we're going to multiply both sides by sine theta. So we'll have r sine theta on the left equals 3. Well, that's nice because r sine theta is just y. And so that's a horizontal line at 3. And once we get into graphing polar stuff, you'll see that that's a horizontal line at 3. Okay, and the last example here is r equals negative 6 cosine theta. So we could square both sides here, but what that's going to do is it would produce a cosine squared, which I don't love because I don't have anything to do with cosine squared. So rather than squaring both sides, I'm actually going to multiply both sides by r. So on the left-hand side, the benefit is that this is r squared. So that can be replaced with x squared plus y squared. And on the right-hand side, the benefit is that r cosine theta has now popped up and can be replaced with x. And that is a rectangular graph in terms of all x's and y's. So rectangular graphs are all in terms of x's and y's. Polar graphs are all in terms of r's and thetas. And to convert one to the other, you use these same formulas that we worked on yesterday to work x's and y's out or to work x's and y's in. As you saw on the back side, it takes a little bit more creativity to go from the polar. These are the options I tried to list, kind of different things to try. And again, there's a little bit of trial and error and getting used to different types of problems. But you saw in the first option, or part A on the back, we squared both sides to get r squared. That was helpful because we used that. We didn't use an identity. Yes, we did. I guess we used an identity because we replaced cosecant with 1 over sine. We took the tangent on both sides in option B and problem B because we wanted to replace tangent of theta with y over x. And then in the last example, we multiplied both sides by r. So maybe something else, creativity, would be needed on your homework, but that's a good start. And at the end of the day, you're trying to get this to come up, r cosine theta to come up, r sine theta to come up, or tan theta to come up. So I'll let you go ahead and get started with your homework. The substitute can project it on the board, or you can go take pictures of the textbook and get started on that at your seat.